All right, well, thanks for coming out, everybody. I appreciate that. So, per the slide, you can submit questions through the entire talk, and at the end, I can start taking them. And if you're not able to get into Slido, we'll just take them through the microphone the old-fashioned way. So, also a special thanks to a couple people before I get started is Keith Krause from NVIDIA. He was kind enough to provide a lot of the slides you'll see tonight. Eric Harper, who's a mentor of mine that works there and has been telling me for months to give a talk about something like this. And the team at MapD, which is a product you're going to hear about a little later tonight. So you're all here for one thing, that's end-to-end GPU computing. And I've been working on this for the better part of the last year because I've started to realize that if you're not utilizing a GPU in your pipeline, even at one point, you are going to pay the price for it, professionally speaking. This can be in a couple different ways. One of them is the time it takes for iteration. It may be taking too long. Personally, it may mean that someone knows something you don't and they jump you in the career ladder. So tonight what I want to talk about is my background, how I got to this point, really start to explain what the GPU is doing and why it took off, and show you some libraries you could use starting tomorrow. So my background is that I'm a data scientist at Meet Mindful. It's an online dating site, and we cater to those who are interested in mindful dating. This includes people who like to cook, who are into meditation, yoga, or just mindful, period. And it's been quite rewarding the last couple months to really dive into the problems, especially related to text and how to deal with really large data sets at scale. It's something I did prior, so working at scale was something I did at my first job, which was as a data engineer plus support. I don't have a beard tonight, but when you get paged at 2 in the morning, those white hairs start to appear pretty quickly when you have 30 minutes to get something done. So I got used to working at scale pretty regularly, and these jobs ran overnight, and it's always been in the back of my head that it could be faster. My area of focus at Meet Mindful is working in deep learning, but more broadly GPU computing. And I'm also a Go AI community member, which is an initiative that started about a year ago, and it has a single mission, which is to get everything on the GPU in your pipeline where possible. So this talk you're seeing tonight starts a year ago, September 2017, because some of my classmates are here tonight. We were all working on our capstones in the room you're sitting in, and I'm part of a Scrum group, as are everybody else. You're broken up during the capstones to work with people within your area of emphasis. And everyone that was working on neural networks knew for a fact, we're going to be on the cloud, you're going to need at least one GPU to get something done. And everyone is getting to the same points at roughly the same times, that we're all pre-processing, we're all having to revisit the extraction phase at some points. And all the other groups are getting there at roughly the same intervals until you start training models. The neural network is something that's very, very computationally expensive, hence needing a GPU, and yet we're training our models faster than people that were running things as simple as a linear regression. It made no sense. There was someone who built a recommender, and it was taking upwards of 90 minutes to go train on a single instance, as opposed to my project, which was 100,000 plus images training in 30 minutes, so 3 models for every one of his. It made no sense. And it got to the point where there was a student who ended up having a breakdown at one point because the company this student was working with ended up giving her a project that was, if I recall correctly, it was 6 to 10 gigabytes of data, and they wanted her to perform k-means clustering on it. It's not something that can be done very quickly, or so people seem to think. So all of that started forming a question in my head: why aren't all data scientists using it? It's a valid question, because we hear about GPUs in the context of deep learning all the time. NVIDIA pushes it extremely hard in that context. But when you think about machine learning, it's executing the exact same mathematical operation over and over and over. And you start seeing that is something that's being executed in parallel, which when people see a little later, you're going to see why and how that gets done on a GPU. So everyone that is a data scientist here, everyone has a career path that is going to start and end with data. I'm a little more cynical, and I think it's going to start and end with a data struggle because it is always a real thing. Everybody, no matter what you're working on, is going to have it, be it the extraction, pre-processing, having to go back and pre-process the entire data set. And it's really not something that's a fun thing to go and deal with, but it's a necessary part of what we do. Now, additionally to that, it's something that over the course of the last decade, we all know about big data, but something else is the complexity of data sets that have started to emerge. It's not just something where you are limited to only running linear regressions, logistic regressions on simple flat data sets. You may be getting something that's at the terabyte plus ad tech data that's very difficult to work with. So anytime we talk about big data, the first thing most people would normally go to a few years ago was Apache Hadoop, and it was because it was the most viable solution. This was something that there really wasn't anything else available, but the problem with it in 2018 is that it is exceedingly slow because you're reading and writing from disk all the time. It's not something that is tenable in 2018. And to people here wondering, well, what's faster, or what else would I do? Well, that would be Apache Spark. And that's been the immediate successor for a number of reasons, not the least of which is that all of your data lives in memory. It's not living on disk. In fact, the most it should ever live on disk is when you're pulling it out of S3 or locally on the cluster. But unfortunately, Apache Spark is not enough. For a lot of data sets, it's not enough for a number of reasons, but when you look at how Apache Spark is working, you're bottlenecked by the CPU. You can run huge instances on AWS with huge amounts of memory. To those that have never done it, I think you can access the X1 instance, which is a terabyte of RAM if you have a ridiculously huge data set. But the CPU is still something that's constraining everything. That is the single bottleneck. And over the last decade, we've really started to see CPU innovation plateau. We saw some breakthroughs with multi-core processing, but those days are long behind us. That is the standard issue CPU you get in every computer. What you're seeing is a SQL query run across a billion rows of data, and you notice that the utilization is really not that great. If you start working on Spark, you will also start to notice that CPU utilization is not nearly as good as it possibly could. And the byproduct of that is you need to switch to something else. You need to go to another form of hardware. Now, those that work in Spark seem to think that you could just scale it out, make the cluster bigger, and that works for a time. Or you can scale it up, and that also works for a time until a bigger problem comes along. So the tenable solution is to go to new hardware entirely, and that is the GPU. What you're seeing is something I took last year at SC17. This is the V100 Volta. 12 times faster than the previous generation. It's absolutely amazing to go work with. And what it's sitting on is a DGX-1, which is one of NVIDIA's supercomputers. 8 GPUs inside of it, and you could actually just rack it, and I think it's, at this point, it's a petaflop of computing power, or close to it. The reason you would use these things is because they are incredibly fast. Disturbingly fast, disgustingly fast occasionally, depending on what you're working with. So what you're looking at is a billion row benchmark. This is a data set consisting of taxi data aggregated from New York from 2009 to 2015. On the right-hand side, you see a Spark cluster. It's 11 nodes, and the hardest query is running in close to 90 seconds. And you will move to something like Redshift, which is 6 nodes, but that is still something that it's a cluster, there's still overhead, there's tech debt, and it does complete faster, but the trade-off with Redshift is that it is SQL only. It's a data warehousing solution, it's not designed for data processing in the context of machine learning. What you would actually do is run a SQL query, pull that data into Spark and do your processing. So by that logic, you're back to Spark anyway. 4 GPUs in a MapD GPU database can execute 1.1 billion rows in under a second. Double that to 8 on the DGX-1, hardest query takes half a second. So you are not sitting on your hands for any length of time. In the context of a billion rows, that's quite something. And what you can do with GPUs on Spark is you can actually have them execute certain tasks, which is, in this context, it would be run a task, then write it back, and run another task on the GPU, then write it back to memory. And this is something that Microsoft was doing with the Azure ML team, and they did see some improvements with it, but it can actually be faster than this. So the reason GPUs are insanely good at what they do is it's how they are fundamentally designed. The CPUs that exist in all of your computers that you buy, they are optimized for serial tasks, which means they execute processes one at a time. GPUs, by comparison, execute thousands of tasks in parallel. And the byproduct of that, for mentioning this with machine learning, is that since it's executing the same things over and over, it can do these tasks very, very quickly. Now, most people seem to think that, again, all GPUs are good for is deep learning. That's not the case, and you will see that tonight. But they are the platform for it. This is what gave rise to a lot of things you will see tonight. So back in 2012, there was the MXNet competition, and the white paper that came along with it is what changed machine learning. Because Alex Krzyzewski, Jeffrey Hinton, and a few others decided it was a great idea to train a convolutional network on GPUs for the first time. And there were only 4 entries in 2012, and what was interesting was that it wasn't just the error rate that got cut in half, but you also see something that goes the opposite direction, that there are 15 times the number of entries the following year utilizing GPUs. The year after that, it doubles. And at this point, if you do ImageNet, it is no question something that you have to do on GPUs. The data set is absolutely massive. And what they showed was that their model that they were running, as computationally expensive as it was training in 5 to 6 days. And for context, at the time in 2012, if you're running it on the best CPUs at the time, it would take you 30. So if I were to start that now, we'd be back next month and look into what those results would look like. If you wanted to train one now, it still takes 30 days. Right now, if you want to change the model and you run this model on the DGX1, I want to say that you can run this in 8 hours. So what took a month can now take a shift at work. Orders of magnitude faster than previous generations of any hardware that's come before it. The other part people don't touch on nearly as much is the accessibility and financially speaking. Before ImageNet, Google built out their own data center. It was $5 million, 2,000 CPUs, and they were pretty proud of themselves for what it could do. After the ImageNet breakthrough came along, the Stanford AI Lab is replicating these results. And what they noticed was the paragraphs discussing the scaling and the theory behind how it could be faster. So instead of using 2, they tried 12. And they succeed in replicating ImageNet, and they succeed in showing that it's incredibly fast. But what they realized is that for the cost, less than the cost, I should say, of a Tesla Model 3, that entire rack was cheaper than Google's entire data center, and it was actually faster than Google's data center. And this ended up getting written up in Wired. It was something that made quite a bit of news, and it only further broadened the scope of what you could do with the GPU, and it drew attention to it. If you're talking in the cost of finances, let's say you've got a $5 million budget. If you wanted to implement something like Google's Brain on the cloud, you have no cost savings. If you try Stanford AI's solution, you are serious money ahead. You keep going down this list and you start to realize that even for as expensive as something like the DGX2, you are still money ahead if you're talking about a $5 million budget. And the DGX2 at the very bottom is something that has 16 cards, 30 terabytes of storage, and a switch inside of it that can run, I want to say it was 1.4 terabytes per second. So in the span of 6 years, we've started to see the speed just grow exponentially. So all that being said, what libraries could you use? So my belief is that the libraries that you see and the libraries that you use need to be intuitive, accessible with really minimal tech debt. It can't be something that you spend hours and hours learning unless there's a great reason for it. And when you have an intuitive library, it just makes your workflow that much easier. You like it, you want to recommend it, and it's something that will only benefit you in the long term. So the first library I want to talk about tonight is PyGDF. This is pandas on the GPU. This was one of the very first things that started about a year ago with the Go AI initiative. And the GPU data frame was that first project. And one of the problems you will see is that every single library has their own type of data structure. But the problem with that is that you run into copy and convert. And some people seem to think that this is a good idea or this is the best solution. No, it's not. There's a better way around it. There's another way to solve this issue. By copy and convert, if you were working in a team of, say, 10,000 people at your company, you are most likely not on the same tech stack. You have to copy and convert, or the team that you're going to throw your model or your pipeline over the fence to go to production, or they're going to throw it back to you for data engineering or refactoring. There is serious overhead in the context of storage and copying and convert. I had to do this recently from Spark, where I had to convert a Parquet file into a Spark data frame, and it took some time. It's really not a fun thing to go and deal with. What Apache Arrow does in the context of PyGDF and other libraries is it's a unified data structure. So it's something that it has zero copy, meaning that you could actually take your data set and go from Kudu to Parquet or Pandas without having to copy it at all. So there is no overhead at all with that. And when you do that, you end up avoiding the CPU entirely. So there is no copy and convert, there's no serialization or deserialization that has to happen. It primarily lives there all the time, and it doesn't impede the workflow of multiple teams. What I see happening with PyGDF and Apache Arrow to boot is you start to fundamentally change the workflow of every single company. You start to change the workflow of every team at every company. Because now, instead of worrying about how to copy and convert data, well, it's all the same, there's no copying involved, and you can get your workflow done even that much faster. And when you start utilizing Apache Arrow on a GPU end-to-end, you're looking at 25 to 100x improvement over Apache Spark. So if you're able to go and put everything in that context, it's just that much faster. It's something that you're able to go and just get your workflow done. There's no headache associated with having to do copy and convert. As someone who knows people that works for large companies, the same as many of you, this is a real pain point, and it can add, at some points, it's added weeks to their pipeline and their production schedule. The next library is CuPy. This is NumPy on the GPU. And this is also fantastic for a number of reasons, because it's not just a low barrier to entry, it's the fact that it's CPU, GPU agnostic. So what you see here is a function with a context set at the first line, and what CuPy is doing is checking to see if there's a GPU available. If there is, it will do this operation on the GPU, and if it doesn't find one, or say CUDA gets updated and it's not compatible for whatever reason, it'll default back to the NumPy operation. So as someone who had to deal with things running overnight or pipelines breaking and figuring out how to fix it, this is something that's huge, because even if something breaks, yes, it will run slower if it's not on a GPU, but at least your entire pipeline does not come crashing down. This satisfies an edge case that a lot of other libraries have not done yet. Third library is MXNet. This is a deep learning framework. It is the one that's been adopted by Amazon more recently. This framework almost became the subject of this entire talk for a number of reasons, but one of them in particular is the fact that it's highly scalable. It's something that's extremely intuitive. It looks like in the documentation, if you were to look at something like the MNIST dataset or Scifar 10, it looks like you're writing Keras code. It's incredibly simple. This library also came about for another reason. It's the fact that I will publicly admit tonight I hate TensorFlow, very publicly. For all the reasons that people seem to think this is a good library, I am the one sitting in the back saying it's not, and speaking freely, you're wrong. TensorFlow fails a lot of things that people don't realize until you go to production, and it is very popular, but the popular choice is not always the best one. So for context, TensorFlow fails a lot of things in exception handling. If you're talking about scaling, it doesn't really do that too well. Do they keep up with NVIDIA's latest drivers? Not so much. Do they keep up with the latest trends happening in industry? Not really. In the context of performance, this is something I feel pretty strongly about, because when I was working on my capstone, I had to stand up a box with 8 GPUs running on it. And I was using Keras with a TensorFlow backend, and it was taking about 40 minutes to train. And if you've ever looked at NVIDIA's SMI, it's something that when you use TensorFlow, it is a memory hog. It will find all the available GPU memory, and it's going to allocate it, even if it doesn't need it. The TensorFlow team's answer to this is that they did it to make it faster. PyTorch and MXNet do not do that. They have way, way better memory management. And when you look at performance, you start to see that as you increase the number of GPUs for something like ImageNet and applying transfer learning with the ResNet 50 model, you notice that the majority of frameworks are faster. Chainer is one, which is one that works with CuPy, MXNet, CNTK, which is Microsoft's. So to those that are wondering, yeah, Microsoft, the company that taught the world to turn computers off by pressing a button called Start, made a faster framework. And as someone who's used it, it's actually pretty good. In the context of TensorFlow really sucking, this is a benchmark from Ben Taylor out in Utah. He runs a company called Ziff.ai. And what you start to see with the exact same model on their data set, that MXNet is getting there in under half an hour. I think that's roughly 5 or 10 minutes if you're looking at it. If you try and run, or what they try to do is run the exact same code base, the exact same model, but they switched it out to use TensorFlow on their back end, it doesn't even get there. It can't even converge to save its life. So it's something that anytime people say, oh, TensorFlow is a great framework, think of this. This is the speed up you get when you have a better library. It's the speed up, and I would say, how would I put this? I would say it's the speed up, the intuition, and the fact that you're going to be time ahead. Recommenders are something else. This was a huge pain point that I've talked with a lot of people from Galvanize and in industry. Recommenders are a unique model. I have an opinion that they are the hardest thing to do in production, because when you deploy them, they behave like nothing else. Normally, when you deploy something such as an image classifier, you pass it through, it predicts whatever that is, and it will get recorded. But recommenders are different because you have to have data sent to it, it has to send recommendations to you, and then once you engage with the data that's been sent, then it has to go and update itself and reprocess on the back end. It's not just a one-way deal with the majority of models that go to production. Spotlight is something that was implemented by a guy named Mashi Kula. He's this brilliant, brilliant guy out of the UK. He has worked for Lyst, which is a fashion company, and he's worked for Netflix, and I believe he's working for Ravelin. What this does is it incorporates PyTorch on the back end, and it allows you to make deep learning recommenders pretty quickly. Again, it's something, if you were to look at this code base, it's something that looks like you're writing Keras, but in the context of a recommender, and a deep learning one at that. It's also CPU, GPU agnostic, so it is something that if you don't have a GPU on your computer, you can prototype it and then kick the job off by changing the flag to use CUDA equals true, and you'll be on your way. It's a really great thing for people that have never built a recommender or want to prototype something. This is an amazing way to go and do it without the overhead of other libraries, and much faster than other alternatives such as Surprise or the linear kernel implementation in scikit-learn. So GPUs would be nothing without showing visualizations. This is PyGraphistry. This is a library that is designed to do network graph analysis. What you're looking at is a port scan attack. So what you're seeing is a couple of, so red circles here are the origin of the attack. You notice they're trying to hit multiple connections and multiple computers at the same time. And what you start to see is that if you were able to take a subset of data from your database, if this is being recorded, you could actually pull this out and visualize to figure out where this is happening and be able to rectify the problem fairly quickly, as opposed to just throwing darts at the wall and wondering what exactly is going on. It's much more sophisticated than that in industry, obviously, but this gives you some serious context as to what's happening and how deeply the problem could be affecting your infrastructure. This library is one that I think if you walk away with nothing else tonight, I think this is the one that you could implement fairly quickly. This is the library. H2O is a company, if people are not familiar, it's a company based out of Mountain View, and they do amazing, amazing work. The original H2O library was something I used in undergrad because it had multi-core implementations of models because I didn't have access to GPUs. So I had to find an alternative that was as fast as I could get it. And this library is unique because it's not just a machine learning library for GPUs. Excuse me. It's a drop-in replacement for scikit-learn. You'll be seeing this a little bit later tonight, but what they are trying to do is replicate as much of the scikit-learn codebase as they can. And the roadmap is something that, I thought that was roadmap for a second. It's not, but that's okay. The roadmap I'll show later is something that illustrates what they're trying to do. The k-means benchmark, if you recall someone having the issue earlier that I had mentioned, if you try and run k-means on 250,000 rows of data, this takes roughly 20, 22 minutes. Single GPU takes 31 seconds. As of April or May this year, that is down to 10 seconds with the latest solver and optimizations. And as you start to increase the number of GPUs, the performance is pretty good, but it's not something that you see huge performance with, in part because the number of GPUs starts to shine when you start to work at scale. If you wanted to do a grid search, H2O for GPU can handle that as well. This is XGBoost running 16 models at once, and it's going to try and pick the best one, or figure out which one would be good for you. 2 best-in-class Xeon CPUs takes about an hour and 15 minutes to go and train that model. If you try and do the same thing on a P100, you can get that entire data set processed across 16 models in 3 minutes. Huge difference. And if you, again, when you start to see the scaling aspect, this is 1 million rows of data by 29 columns. So when you start to see that, as you start increasing the number of GPUs, you start to notice the scaling start to take place. Now, the aforementioned roadmap is something to consider because they've implemented a number of things you see on here. PCA and SVD out in Q4 2017, those are in. And as someone who's used both of them and has had to wait maybe a grand total of 60 seconds for anything he's been running, it's absolutely amazing to go have that and not have to wait hours to get something to work. If you look at 2018 to 2019, there are a lot of things that are going in. I am eagerly awaiting TF-IDF because that's something that can take quite a bit of time. Word2Vec and Doc2Vec are also coming in. H2O is throwing their hat into the ring with this. You can implement something like Word2Vec and Doc2Vec in many other frameworks, but not all of them are necessarily on the GPU. And some of the recommender systems are going to be added as well. The one thing that I do have some interest with is automatic K, meaning that it's going to choose K number of clusters for you before the model's even been trained. So I'm curious about what exactly that's going to do moving forward, because picking the number of topics for something like latent Dirichlet allocation, picking the number of clusters for any problem you may face is an art. And I'm very curious to see what AutoK is going to do in that context. So that being said, I want to show a couple of demos. You guys have waited long enough. And I wanted to show a couple of them off at this point. And I think the first one to start with that's appropriate is Graphistry. So the first thing I'm going to do is just go in and load my credentials. It's worth mentioning that the API key to work with PyGraphistry is free. It takes about a week to go get, but you end up having... Oh, I say thank you. Appreciate that. Better? it's worth mentioning you can get this key in about a week, and I think the limitation is 8 million edges. So it's something you can run a pretty huge graph through it. In this context, I'm working with the movie lens dataset, and I'm going to load up the 20 million ratings. I'm not going to be running all of them due to the limitation, but what I am going to do is take a random sample of it and then start to plot the ratings graph. So what this is doing is it takes your sample of your data set, it's actually sending it over the internet to a GPU cluster and returning it fully rendered and ready to go. It is coming, be patient, we'll do that. So one thing I should mention as well about this library in particular, Graphistry is interactive. Most network graphs, if you're looking at, I think Network X is one, and it's not Giphy, there's another one. It's another name, I think it's Gephi, that's the correct pronunciation. They're not interactive. This is one where I can zoom out, I can move it around, and I can even start to zoom in and take a look at the nodes and edges in real time, which is really, really, really nice. And what you start to see here, if no one's familiar with graph theory in here, it's comprised of nodes and edges. And if you're doing something like a collaborative filtering recommendation system, this would make some sense. You have users and you have items. In this context, you have users who are rating movies. So, for example, I can start to zoom in just for kicks. I can take a look, and you start to notice there are a number of dots here. Each of these are individual users that have rated some movie. In this case, the movie ID is 296. What I can do is plug that in for curiosity's sake, and you find out that it is Pulp Fiction. And it has 336 reviews just within this sample space alone. Conversely, I can pick something else just for curiosity's sake. Dances with Wolves has 231. So this is something that's actually pretty cool to look at the center of something like a network graph. Something else you can do is look at the far end, because when you start looking at the edges of this graph, you can start to find some really fascinating things, and in industry, you may find some edge cases you weren't expecting. So what I'm going to do is take a look at something like this, because there aren't really that many. You see that there are 2 users that have rated one movie, which is the ID 1750. If you start to plug that in, so it's StarKid. Now, granted, this is something that is out of sample, but it is something that I might expect that to have more reviews, but this is a sample size of 100K. But what Graphistry gives you is the ability to render something incredibly quickly, beautifully, and it's fully interactive. I have tried to render something like this in Network X. 1, doesn't look nearly this beautiful. 2, it takes about an hour to do it with the data set that I've got, including this one. It's not a fun thing to go deal with when you're sitting on your hands. And the ability to have this be interactive and work with it fairly quickly is super, super invaluable. So the next one I would show is Apache MXNet, because content recommenders are something I see a lot of at Galvanize, and it is something that does and has amazing potential. But the problem is with content recommenders that are memory-based is that when you start to add in more items, more people, it's something that means you get to train the model again, and that may not be a tenable thing. Or if it gets really big, you start thinking, oh God, I've got to go to Apache Spark. That is not the case. It's something you can actually do fairly quickly. So what I'm going to do is import sample data. This is only 500 rows for context. You can train this across a huge amount. But what I'm going to do is run the sklearn tf IDF vectorizer. Granted, this will be on the GPU soon, but I'm using the sklearn implementation for the time being. Then what you have to do is compute something called cosine similarity. And for people that have never built a content recommender, it's the way to look to see what items are going to be the thing that should be recommended to you. So if I run that, the sklearn implementation is 44 to 52 milliseconds. On this run, it can be faster than that. What I can do is take the matrix that was computed with the TF IDF vectorizer, and I can send that to the GPU as an MXNet ND array, you'll notice that I have a parameter here called CTX. That's called context. And what this means is it is living on the GPU. It's something that's not going to leave it until I tell it to. What's even better than that is if you're running a cluster or a box with multiple GPUs, I can set the context down to the specific GPU I want to run it on. So if I want to run it on the first, the second, the third, it doesn't matter. There are some cases where you'd want to do that, and you end up starting to work with it pretty efficiently in that context if you're running out of GPU memory or you want one GPU to only be available to do one thing specifically. So once that's done, you can implement a function, mx cosine distance, which is just the dot product of the array and the transpose of it. And when you time that, it's pretty darn fast by comparison, and even on multiple runs, what you're starting to see is that it can get pretty low pretty quickly. 572 microseconds as opposed to milliseconds, and that may sound like it's non-trivial, it may sound like it's not really that big a deal, but it's 91 times faster than the CPU implementation, and that's only on 500 rows of data. When you start to scale this out to the millions, it gets returned in minutes as opposed to hours. And if people don't believe me, well, this is what sanity checks are for. That I can look at the CPU implementation and look at the first couple of values in the array, and I can look at the MXNet implementation, and they are identical. You'll notice that the ND array has been shifted slightly, but the ND array, you'll also notice at the very bottom here, shows the GPU context, so it is running on the GPU. We're not done with that yet. I want to get the recommendations out of it. So in this case, I want to look at the ID 10, first thing that comes to mind. And I want to take the MXNet recommendations and take a look at that. Actually, let me take a look at 5. I think 5 might be something that's, yeah, the wind jacket. So I can work with it and show that even with the ID of 5, it gets your recommendations back fairly quickly. And if you change that, you get the recommendations again. It's something that's pretty darn fast, and it's something that if you're ever going to implement a content-based recommender, this is one of the very best ways to go. The linear kernel is awesome in sklearn to learn on. It's not something that's tenable in a production pipeline. And what this means for recommendation systems is that content-based filtering is not out of reach. Collaborative filtering is normally the thing most people go to, but collaborative filtering has the issue of cold start. You can't recommend things to people that have no data. That's where content-based filtering comes in, but it's incredibly hard to go and train the model, and it's something that's normally not tenable. And now it is. It's something that you could start to incorporate that in your pipeline at the outset if you really, really wanted to. So if people are also wondering, why am I switching things around? For whatever reason, my computer does not like running concurrent tasks. So I have to stand up different Jupyter Notebook contexts when I'm doing this. The next one I want to show is PyGDF, just to show what you can do with it. And really, I would say, how easily you could adopt it in the pipeline for a majority of things. So what I'm doing is importing it via pandas, but I want to convert it to a GPU data frame and get to work with it. So I think the context of this is it's not housing data, that's the next example, but it's something close. I believe it's something close to it. It's income related to people and some of the demographics around it. That's what it is. So what I want to do is take a look at the GPU data frame, and I can convert it back to pandas if I really want to, and look at it. Looks just like pandas, right? It's something that's pretty straightforward. I can also modify the data types moving right along, and in this case I want income earned and the second feature here to be float 64, not integer. There is a time and place for integers, just not for this example. And what I also want to do is show that the income is actually correct. The current income earned in this data set is not correct. So what I can do is change income earned and apply the function defined above, and I can do that pretty quickly. And once again, it runs And on top of that, you have the ability with a GPU data frame to sort values. Again, same method that you would see in Pandas, sort values by a certain column. Multiple can also be specified. And now you run into an edge case where there are negative values, which leads into the fact you can either query or filter it out. Again, very similar to Pandas. I believe, for folks that don't know, Pandas has the ability to run, you can run SQL inside of Pandas. I think there's a library, it's either Pandas SQL or something similar to it, so you have the ability to filter it out in a similar way. You can also one-hot encode. This is going to my knowledge, this is going to become something that will become a main method later down the line. But you have the ability to convert it. And now the data frame has been blown out, or so it looks like to folks that have never worked with Pandas before, have to do one-hot encoding. This is something that has to happen. And now what I can do to train a model is I can go and split this into separate data frames for training and validation. I'll just use the classic 80-20 split. And now what I want to do is turn the GPUs into a GPU matrix. And then I have to obtain a pointer. And this is something that, per documentation, it's not something that's going to be necessary in the future, but it is something that is necessary for now. So what I can do is train ElasticNet, which is pretty cool. But the one that I want to train is clustering with k-means. Actually, wait a minute. Did I import? Hang on that. That may have been it. Hold on. Interesting. There we go. So for whatever reason it was not imported, that's okay. You can train it, and k-means runs fairly quickly. There's another example you'll see. And what you have the ability to do is, again, cluster your data very quickly, and moving right along, you can even implement something on here with GPU data frames, such as principal component analysis, run it fairly quickly. You can even go as far as XGBoost. And again, runs fairly quickly. The one thing I will mention is that right now with something like H204 GPUs, you notice that it is a CPU matrix. What has to happen currently is it has to be serialized back to something that lives on DRAM. That is going to change fairly soon. So I think, let me see, I'm actually good on time, which is fine. Let me see. Yeah. I'm gonna run one other because the k-means clustering thing that happened a year ago, that was something that gets to you because you realize that the person was not limited by intelligence. It's one thing to be limited by your intelligence, it's another to be limited by the technology of your time. And Geoffrey Hinton's a classic example of that. It's someone who now is just starting to see the fruition of his work in deep learning, and it's all coming to fruition at the same time across so many different industries. So this example is home site data from a Kaggle competition, and what I'm going to do is rerun this, and if I were to rewrite this code, I would probably do it end-to-end in PyGDF. What you start to see is you're converting the code in the pipeline to accept only numerical values. K-means and many other algorithms do accept that, and it's the only type of value that they can accept. Let's see. So it should get done in a couple of seconds. So now that it's been pre-processed, just for context here, I am going to look at it. It's 260,000 rows in the training data set. I've got a GPU in this computer. I am going to cluster 250,000 rows of data. For reference, that benchmark you saw was 30 minutes on a single CPU. On a single laptop, you can get this done in about 5 seconds. And it's worth mentioning, this is the same implementation as scikit-learn. There's nothing changed on the back end. There's nothing that would have altered this in any way. It's the exact same type of model. There's no difference between it. If you're really bored, I would encourage you to run this on sklearn. It will not complete in an hour. Let me go back to this. We're almost done. Let's look at that. So I want to go and revisit this question, because this is something with the amount of examples you have seen tonight. After a year of working with GPUs, what are some of the conclusions I've drawn from it? Why aren't all data scientists using these things? One is the knowledge gap. The amount of things you've got to learn as a data scientist is huge, and it never ends. It's what you sign up for when you take this type of career path. The knowledge gap is a really big one. I think people realizing that there's more to machine learning than just neural networks implemented on GPUs. Yes, neural networks are fantastic. As a deep learning junkie, it's an amazing, amazing model, but not everybody uses them. The second thing is management. I think one of them, when I've spoken with other people along the way in the last year, this is something that has become a huge pain point, because you have some up-and-coming data scientists on your team, and they have the ability to make your pipeline blindingly fast, and management puts their foot down for nothing less than just saying, because I said so, or we're not doing it, whatever it may be. These have been some reasons I've heard from other people in industry, and it's something that doesn't just kill your creativity, it's something that really doesn't make you want to go and implement something at that company. You can talk to them as much as they can, but it's something that if they're not going to listen, it's not necessarily worth something pursuing. And what I've also seen is it's the perceived amount of time you have to spend learning other libraries. And what I've shown tonight hopefully bridges that gap. It gives you the ability to go and do that. With GPUs, it's something that as I use them every day on my computer, in the cloud, and on a desktop I use at work, it's something that you start to realize that you're not limited by time. You are now limited by your own ingenuity and the ingenuity of your own team. It's something that you have the ability to go and implement huge amounts of models with something like H2O for GPU. You have the ability to go and iterate faster, but what that does is get your creativity going. It's something that you don't have to worry about waiting for a model to finish. You don't have to worry about if it's going to fail. As someone who's dealt with the pain of Spark clusters more recently, I can tell you that it is a huge pain to deal with, and don't really want to deal with it too often. And it got to the point where I ended up rewriting something for the GPU because it was taking too long. The model I was using was latent Dirichlet allocation, and it was taking about 40 to 60 minutes, and then running the same model on a couple of GPUs runs in a couple of minutes. And the byproduct of that has been something that not only gives you more meaningful features with the model I ran, but you get your results faster, and I can go and reiterate. But there's a way to roll this up a little bit more, if you'll indulge me, is the fact that they do help you accomplish your life's work. This is something that Jensen Huang, who's the CEO of NVIDIA, has talked about often. Anytime you see him speak at GTC or in interviews, this is something you hear about pretty often. And in this context, I'll share one story from mine because it's related to the project I did last year. And the project, for people wondering, it was a neural network to detect blindness in diabetics, and it seemed to go over pretty well. But there's also the part in life that you don't control. And what ended up happening was Suraj Ravel, if people don't know who he is an AI YouTuber, somehow got a hold of my repository. I don't know how he found it. I don't know where he got the idea to go use it, but he made a video about AI in medicine, and he featured the repository. And the byproduct of this has been people not only cloning it and working with it, it's resulted in helping some teams in India try and re-replicate my results. But the thank yous I get from places such as India, China, I think I've gotten one from Israel, the thank yous are amazing, but beyond that, it's something that I've received some other emails where they say, thank you, you have now made me want to go and pursue deep learning. This project is a thing that now makes me want to pursue that career path. That carries a lot more weight to it. And it's something that you start to realize what's the common denominator. It's not just the fact that they're interested in deep learning, the fact they want to do good things with their life. It's the fact that the common denominator was the GPU, because that project I built does not exist without it. It's something that without it, there is no project, there is no way to assist people in getting where they want to go in their career path, or just running something because they were interested in learning about something like deep learning. Now that being said, I have one more thing. So the last example I want to show tonight is from a company called MapD. They're based out of San Francisco. It's a GPU database, and it's pretty cool. So the benchmark that you saw is over 1 billion rows of taxi data. The last couple of days I've been working to get something to show you 1.46 billion rows. And it's worth mentioning that this is a SQL database. They also provide visualization. So this is something that you don't really get to see too often. They have some other examples if I have time, but what I want to do is go and grab it. All right, so it's back up. Let me see. So what you can start to do is I can change it, and it's interactive. So if you're wondering what this is doing, this is querying 1.5 billion rows of data, and it's able to re-render what I want to do in near real time. So you have the ability to go and visualize and get your answers in a way that you never have before. This is a SQL database, people. So it's something that you could actually port your existing database into MapD. You can utilize the power of the GPU to get results that you otherwise wouldn't be able to get anywhere near this quickly. MapD has also got a SQL editor. I think this should run, but let me take a look. So what that just did is it's looking at cab type and it's counting them all. If people have done aggregation in SQL, you know they can get pretty expensive. This queried 1.5 billion rows of data in 30 milliseconds, and you can get even crazier than that, which is doing even more complex aggregations. So what you're going to see is passenger count, the year of the pickup, the distance of the trip, and I want to count all of them. And I think there's actually another one. Give me a minute. I believe that I have the query here. So half a second can return 1.5 billion rows of data. So I am someone who is not happy unless I have all the data all at once, all the time. This is a pretty damn good solution to something like that. So that being said, that's the presentation. If you've got any questions, I'll take them now. Hey everyone, it's Greg here with one final demo. This was one that I left out in the interest of time, but I'm going to put it in after the fact. One of the libraries that I did not touch on is PyMapD, and as you can guess, it is a Python library that allows you to interface with MapD databases, which is pretty cool. So I want to show off a near end-to-end GPU pipeline using PyMapD, PyGDF, and H204 GPU. So we'll get started. First thing I'm going to do is import the necessary libraries, and then I'm going to instantiate a connection to the database. The user is MapD, the password is the password I've defined, the host is where the database is living, and the database name by default is MapD. So I'm going to create a connection to it. Then I want to get the tables from the database. Now there are 3 that are included with the AOI by default, but the one we're going to use today is trips, which is the one I showed off in the video you just saw. Then what I'm going to do is create the query that will pull the data out for us to train the model. This time around, we're going to be predicting total amount, and we're going to do it using passenger count, precipitation, and trip distance. And I'm going to pull out a million rows for time's sake. I'm going to define a cursor and then execute said cursor. Now, one of the things you'll notice is that this looks like a fairly cumbersome workaround, and it's because I don't have something currently working on my computer, which is the select IPC GPU method. Inside of PyMapD, what you can do is specify the SQL query in a string shown in the documentation and what I've shown. But what you can do is use that query and pull all the data from a MapD database directly to the GPU on your computer or another EC2 instance, which is really cool. And if you don't have a GPU, you can pull it out using the select IPC method into a Pandas data frame versus a PyGDF GPU data frame. So once that's done, I am going to pull everything into a GPU data frame called trips. I'm going to look at the first 5 rows, and you see that the data is there. Then what I'm going to do is split the data into training, validation, and test. The first thing I do is enforce float64 data types on all columns. I specify the train and validation split ratios, define the split point, break the GPU data frame up based on that split point. And once that's done, you notice that it is an 80-20 split. Then what I do is convert the GPU data frames to GPU matrices. Moving forward, you will be able to use a GPU data frame as input, but for the time being, I need to convert it to a GPU matrix. And that executes successfully. I also have to obtain pointers for the time being. Again, this step is not necessary in the near future, but for the time being, I do need it. Then I'm going to train the XGBoost model. And inside of H204 GPU, what you want to do is specify the backend as H204 GPU. This is going to allow you to execute everything using the GPU. However, you do need to convert the GPU matrices to CPU matrices. The reason for this is that at the time of this recording, H204 GPU does not support the GPU data frame. It's expecting it to be in a CPU matrix form, so I have to convert that. Additionally, I am going to set the base parameters you see in the XGB params dictionary, and that's taken care of. And then finally, I'm going to fit the model using the CPU matrices we defined above. And then I can just get the first 20 predictions. And there you have it. That is near end-to-end GPU processing with PyMapD, PyGDF, and H204 GPU.
How come you didn't mention Numba?
Numba is one that's extremely good for what it does. It's the fact that I find Numba not to be as intuitive. It's an important library, and it's awesome. It's absolutely awesome at what it does. But it's something that, in the context of this talk, what I wanted to do is give people accessibility. And when you start to look through Numba code, it's not something that feels the most intuitive. And you start to deal with some overhead, which leads into potential tech debt. You lead into some other things. So that can be difficult.
What's your experience been with kind of the rapid nature of these libraries and all that? So Arrow is starting to mature, MXNet is mature, but like PyPy and PyGDF and so on. Can you describe your experience there, like how much maintenance you've had to put into changing your code as libraries evolve, or how the documentation is?
So I utilize them when I know I can get the majority of it done. If I can get 70-80% of my workload done, I can do that. The pull requests that are coming through are fast. That's the thing, that there's active development behind it. My experience with it is that there are a couple of outstanding issues with each library. I think one of them more recently was some issue with a join in PyGDF, but that has an outstanding pull request that's supposed to get merged. And that is some of the overhead. So you do have to do your due diligence, you do have to be careful, but the byproduct of it is that if it does work for the majority of things you want to do, then it could be a pretty good solution. It just depends on how big your data set is and if you really need it. But that's my experience with it. Has been something that there are a couple workarounds you need to do, but they're not showstoppers, so to speak.
You mentioned LDA. Which implementations of LDA are GPU friendly?
So there is one that people can go look at. There is a version of topic modeling for the GPU using Keras, and it's in the form of variational autoencoder. Right now, to my knowledge, there isn't an LDA library available. The one that I implemented is similar to it. That's the one I'm describing, but there are a couple of custom things inside of it that do what I need it to do. So there is no LDA implementation to my knowledge just yet.
What's the story with MapD as far as like if you have more data that fits in GPU memory?
Great question. Yeah.
I read that article with the benchmark, and it's like it takes like a pretty substantial amount of time to load the data in MapD. And so it seems like a not fair comparison with something that's like designed to persist data like on disk for like warehousing.
Sure, it's something that for MapD in terms of how it handles it is that if it does not have enough GPU memory, it is going to spill over to your DRAM. What it also does is, depending on the amount of queries that are being executed, it tries to optimize what is kept in the GPU and what is not. So if you are working in a team of say 1,000 people and they're all running either similar queries or something to it, odds are there are certain tables you're querying pretty often, and everyone is querying them pretty often. So it will allocate it and optimize it for that. And it's something that my answer to it, to people wondering, if it's not a fair comparison, I look at something like this and see the future. I don't see something that is just for a niche group of people. I see something that would, for many people and many companies, this is something that they would want. Especially, I have a friend of mine who works at a hedge fund, and that's something that for them, I don't know if they're using this, but for some of the data that they're pulling, some of the things they're using, being able to have it that quickly is a really big deal.
Yeah, I mean, I just know there's other people working on like GPU acceleration for like Postgres and more traditional databases that are getting similar performance. And it just seems like you have a lot better story there about like moving things on from disk to GPU and back to disk, and whereas like MapD is kind of a clean sheet implementation, which I think is awesome for the GPU part. I think that it's like a more fair comparison, right? It's probably like custom hardware accelerated, or in-memory databases, which probably cost about the same to run and are almost as fast.
Well, the other question is how long do you want to wait for your data? Have you ever had, just for curiosity's sake, have you had issues with your job running huge data sets or dealing with things like that?
No, I mean, I think most things, right? It's like getting things on the one machine is a big win, right? Like when compared to something like Spark or Hadoop, right? It's like most people are using that ecosystem not because they need it, but because it's popular, right? So it's like getting stuff on the one machine is really fast, right? Whether that's your machine or like one big EC2 instance, and it's like after that, tool to use around it. I mean, I think you present really interesting use cases that I haven't thought about that much, but like, I guess what I see all the time is people are like, oh, I have like a 5 instance Spark cluster. And it's just like, why? Like you have like 10 gigs of data that fits on your, your Mac, great, right? Like, I think that's you kind of get into the gospel of like Java big data, and that's, to me, that's more the issue, not CPU or CPU. It's like Java big data, like gospel, and breaking out of that.
So it is something that, there are implementations of Spark that are unnecessary. Spark is by design built for necessity. It's not just you will never hear a team of data scientists say, "Yay, let's go to Apache Spark." No, it's the last thing that most people will go to. It's not something that most people would want to do. The reason for things like MapD personally, or when I use it for my own work, is the fact that I can't wait. There's work that actually has to be done. To anybody that is working at scale, who has felt the pain of Hadoop clusters, who's had to deal with tech debt, who's had to deal with a cluster either being down or not being performant, who is dealing with Spark context and having to set the number of executors and the number of cores and the amount of memory. There is no silver bullet to it. The Spark team seriously thinks that is okay. And that's something where if you have to spend that time doing it, that's not something that you want to be spending your time doing. To your point, I would much rather have it on one machine and eat the cost, because it's something that you're going to get your results fast, it lives there all the time, and you are not only going to sleep better at night, but you're going to get your data that much faster. Staying with Spark clusters is just not, as someone who's done that and maintained it, it is not a fun thing to go do. So.
Which libraries do you think have the best capabilities for architecture systems?
Say that again?
Sorry. Which libraries do you think have the best capabilities for architecture systems?
So you will find implementations with them in various frameworks. I think that, so if people are getting started with it, I would say the CPU would be something such as Surprise and the linear kernel. When you start to move into larger data sets, I would say Spotlight. And you can also find implementations in other deep learning frameworks. You can find them in MXNet, you can find them in Torch, in TensorFlow if you're daring enough. There's a number of ways you can do it. And of all of them, I would say start with Spotlight and then look at a couple of those other ones, because they will, it'll serve you really well. It's something that you can get started with it. You don't have to think too hard or write a whole lot of code to get going. So start with Spotlight and then look at some other frameworks, such as, I would say, MXNet and PyTorch. Don't look at TensorFlow. I made that clear. Don't. So.
What's your, if you have to make a rec between, like a data science team wants to get going with GPUs, between getting machines that have powerful GPUs, like at your workstation versus using cloud stuff, what's your perspective on that?
I would say the cloud, because it's the fact that everything is fully baked and ready to go. It's something that you can also get going a lot faster. If you buy something like the DGX station or anything from NVIDIA, that it all comes prepackaged and it's going to work, but the cloud is something that's just so tenable that even for when I was working on developing the MapD database, I started with a couple million rows of data on a single GPU, and then I turned it off and changed the instance in a couple seconds and turned it back on again. When that got too big, or too small I should say, I ended up turning on another instance and reallocated it. So it's something that just to have that ability to go scale quickly is super important. And the budget is well spent there because you have access to everything. But yeah, you may buy one server with a bunch of GPUs in it, fantastic, until the problem set gets bigger or you need it to be faster. That's where the cloud can come in. So I would say the cloud, and then if you want to do prototyping, I would recommend getting a laptop with a GPU, or you buy an eGPU enclosure and get something like a 1080 Ti, $700 if you can find one, and that would be the second thing. But the cloud would be where your money's best spent.
Library demo, really cool, and 1.5 billion in 30 milliseconds, that's awesome. The other part of doing data science is processing and cleaning, like you mentioned up front of the slide, right? The whole data challenge. What about doing that on GPU? Are you seeing similar kinds of speed increases, or is that also still going to be a bottleneck?
Yeah, it's something that I think it's going to be something that we see more of as the libraries become better developed, because something like PyGDF, great example, is that there is pre-processing you can do on the GPU, and it does exist. But it's something that isn't as mainstream because the data sets either aren't big, or the majority of documentation, when you look at it, it will just say, well, go to something like Apache Spark, and it'll take care of it for you. I think we'll start to see it as the libraries become more mature and developed. The TF idea of vectorizer is something that I really do think is going to bring this to the forefront, because that's something that can take a very long time to go and do. And if you can implement that across tens of millions, hundreds of millions of rows very quickly on 8 GPUs to say the least, then that starts to bring attention to other areas of machine learning, because a lot of the focus with GPUs has been deep learning. But once you start seeing crazy benchmarks with other data sets, so something like the taxi data set, it's not deep learning, it's business intelligence plus reporting, and some SQL queries along with that. You start to see benchmarks with natural language processing, then you started to draw more attention to the entire ecosystem and the entire population of data scientists. So with pre-processing, that's something that, having experience with it and having done it, it will get there. It just has to be given a little bit more time, but it's going to get there.
Awesome, it's a great hand.
Thank you.